Hello again to another Agricultural React, and today we'll be watching two people we are all related to from PBS Eons. And let's just get into it, and I'm guessing they're gonna be alluding to like an Adam and Eve thing.
You have the materials inside you right now to unlock the story of your deep, distant ancestry. And also mine. That's partly because you have mitochondria in your cells, and you got them only from your mother, not your father. And if on your 23rd pair of chromosomes you have an X and a Y, like I do, rather than an X and an X, then you got that Y chromosome only from your father. Together, these two facts mean that there's an unbroken line of mothers and mothers' mothers who passed down the DNA in their mitochondria for hundreds of millennia, creating a biological thread that connects you to a single female ancestor, regardless of your gender. And it also means that there's a lineage of fathers and fathers' fathers who passed on their Y chromosome uninterrupted, leading back to a single male ancestor. Okay, now I know what this might sound like. I'm not talking about the first two people. I'm talking about two humans who lived at different times in the distant past, about 200,000 to 300,000 years ago. I'm talking about two people who never met, but who, because of this odd quirk of genetics, combined with some unique evolutionary circumstances, managed to pass on a very small fraction of their genomes to you, and to me, to all of us. And this is an incredibly powerful tool for studying where we all came from. We're only beginning to understand the legacy of these two people to whom we're all related. It's a legacy that goes back some 10,000 generations. Let's talk about where this legacy begins in your own cells. Your mitochondria are the small structures that produce energy for your cells. And they're relics from a time more than 2 billion years ago when our ancestor was single-celled. And at some point, it engulfed another single-celled organism and started using it as an energy supply. As a result, mitochondria today still have their own, if very short, genomes. This is your mitochondrial DNA, or mtDNA. And it's only passed down from the mother because egg cells have lots of mitochondria, but sperm cells only have a little, and they're destroyed after fertilization. Meanwhile, the Y chromosome is the smaller of the two sex chromosomes, X and Y. People with an X and a Y instead of two X's are physiologically male. And there's a reason we study mitochondrial genomes and Y chromosomes to understand our ancestry. Actually, two reasons, because they have two important things in common. Their genomes are both pretty short, and they also don't recombine. Okay, here's what that means. In the process of creating sperm and egg cells, our chromosomes line up and exchange information. Matched pairs of chromosomes swap arms or legs with each other. This molecular do-si-do is known as recombination, and it means that offspring will have slightly different combinations of genes on each of its chromosomes than its parents had. This is basically how sex creates new genetic variations. But Y chromosomes are much smaller than X's, and unlike the rest of our chromosomes, it doesn't match its partner, so it doesn't recombine with the X. And the mitochondrial genome doesn't recombine with anything either, because it doesn't have a partner to combine with. All of this means that these two snippets of genetic information get passed on almost unchanged from parent to offspring, which makes them traceable through time. So for decades, scientists have been studying these two bits of information, and they tell two stories about our history that are slightly different but still complement each other. For example, one of the most important things we've learned about ourselves from mitochondrial DNA is the story of human migration. Even though it's passed on from mother to child without recombining, mtDNA does slowly accumulate mutations. And as those mutations get passed on within a population, they start to form a genetic pattern within that group. This allows scientists to organize us into genetically similar groups called haplogroups. Anyone who's used a DNA test kit has heard of these. So if you and another person share most of these mitochondrial mutations, then you belong to the same haplogroup. And decades of research into mtDNA has shown that the vast majority of haplogroup diversity exists inside Africa. For example, there are several haplogroups that are only found in Africa or among people of African descent. These are groups like L0, L1, L2, and L4, 5, and 6. But the whole rest of the world is represented by parts of only one haplogroup. That's L3. So if you're of non-African descent, you belong to L3, which contains lots of subgroups like K, M, N, and R, which are found among populations outside Africa. But there are even more subgroups of L3 found within Africa. So what does all this tell us? Well, for one thing, it's taken as genetic evidence for what's known as the out-of-Africa hypothesis. The hypothesis that modern humans originated in Africa and spread throughout the world. This model was first developed by anthropologists around the 1980s, based on skeletal evidence. Specifically, the earliest anatomically modern humans that were found in southern and eastern Africa. And today, this mitochondrial data is seen as molecular support for that idea, starting with a famous paper published in the journal Nature in 1987. That paper detected the first signs of these genetic patterns based on mtDNA sampled from just 147 people from 5 different geographic populations. But among other things, that study showed us that there's such a great diversity of haplogroups in Africa because that's where our genetic populations are oldest. So when a small group of people migrated out of Africa, they only represented some of the genes in the total human gene pool. Those migrants became the founders of their own genetic lineages found within the haplogroup L3. But there was still an older source population in Africa that they used to be part of. Now, we can also use changes to our mitochondrial DNA to estimate when certain lineages split off from each other. This method is known as the molecular clock, which we've mentioned before. It's based on the idea that mutations occur in mtDNA at a pretty regular rate. But since that rate of change isn't the same across all of humanity, the clock needs to be calibrated, like with the help of well-dated fossils and even the DNA of ancient fossil humans. Using this method, scientists have traced the mutations in all of the major lineages of people from haplogroup L3 that appear outside of Africa. Where those non-African groups converge in time, we find the earliest humans that left Africa. And the data suggest that this happened around 70,000 years ago. And going back even further, it appears that all known haplogroups converge at a single female ancestor who lived roughly 200,000 years ago. So our mitochondrial ancestor can tell us a great deal about where we came from and when. But we also have to talk about what she can't tell us. She isn't the first woman of our species, or the first anatomically modern human, or anyone really special for that matter. For one thing, there's evidence of modern humans as far back as 300,000 years ago in northern Africa. So we know our species was around long before this woman lived, for thousands of generations. But their mtDNA just didn't make it to the present day. The fact that one woman passed on her mitochondrial genome to all of us is really just a matter of chance. Think of it this way. In any given generation, a woman might have sons but not daughters. And if she only has sons, that means none of her mitochondrial DNA will get passed on. So our mitochondrial ancestor is the only person who managed to have one or more female offspring, who in turn also had female offspring in an unbroken line for the past 200,000 years, by sheer chance. Now, naturally, there are a lot of limitations to what mtDNA can tell us. The dates it provides us aren't very precise, and the genomes themselves are small, representing a tiny fraction of the information that's in our whole genome. And of course, they only tell us about half the population, females. So while mtDNA was crucial as an early source of genetic data, as sequencing methods started to improve, scientists began studying the other non-recombining stretch of DNA, the Y chromosome. And much of this work was done in the early 2000s. And just as mtDNA can shed light on the growth and spread of certain maternal bloodlines, the Y chromosome can tell us about the migration patterns of some groups of men. For example, a pair of studies in 2010 and 2013 sequenced both the Y chromosomes and mtDNA from 2,740 people across Indonesia. And the results showed that a surprising amount of Y chromosome DNA came from far away, like China, India, Arabia, and even Europe, especially in Indonesia's western islands. On the island of Borneo, for instance, the presence of the Y haplogroup known as OM7 seems to be the fingerprint of immigration of men from Han Dynasty China about 2,000 years ago. But in those same men, their mitochondrial DNA more closely resembled local haplogroups. So that suggests that, at least over the past few thousand years, men have been arriving from elsewhere and pairing up with local women. And when it comes to how far back this Y chromosome goes, the latest molecular clock calibrations now suggest that our Y chromosomal ancestor lived about 200,000 to 300,000 years ago. Much like with our mitochondrial ancestor, this guy must have had at least one male offspring, who in turn had more males, in an unbroken line for hundreds of millennia. Now, we don't really understand why these two individuals left the indelible mark that they have in our genomes. One idea is that there might have been a boom in the human population around 200,000 years ago in Africa, when our species happened to be doing very well for itself. If that were the case, then the offspring of both of those people may just have been more likely to survive and pass on their DNA. Or in the case of our Y chromosome ancestor, it could be that he had a sort of Genghis Khan thing going on, having many kids, some of whom were sons who also went on to have many kids. But the story that these two people can tell us ends when they were born, because we can't trace their genetic trail any further back in time. So to probe the origins of anatomically modern humans, we need earlier sources of data. Remember, the Y chromosome and the mitochondrial genome represent just a small fragment of the human genome. So to understand the whole range of human diversity, we need to study the whole range of human diversity. Luckily, this is the 21st century, and we no longer have to sequence tiny stretches of individual genomes by hand. We can sequence whole genomes, and quickly. So as our technology and methods improve, we may soon be able to reach beyond the lives of these two ancestors into the even deeper past. But even when we do, each of us will continue to carry the molecular legacy of one man and one woman who managed to make their mark on all of humanity.
That was very interesting.
Thanks for joining me today for this truly amazing story. And big thanks to our eontologists, Jake Hart, John Ivey, and my boy Steve. Now let me give you my 2 cents. Actually, 2 Cents is a new series from PBS Digital Studios about money and you. Financial experts and husband and wife team Philip Olson and Julia Lorenz Olson guide you through the complex world of personal finance, from the kitchen table to the stock exchange. You'll get practical knowledge about how to spend, save, and earn, and even insights into how your brain is hardwired to react to economic problems. Money might make the world go round, but it doesn't have to make your head spin, so check out the link in the description and subscribe to 2 Cents. Now, what do you want to learn about? Leave me a comment and don't forget to go to youtube.com/eons and subscribe.
So I have some time on it. Okay guys, what do you think? Yeah, well, the title is kind of says like, well, he started off with the video saying it's not what you think it is. So yeah, it's not like Adam and Eve thingy. But it is very interesting saying that basically we all have one proto-mother and one proto-father that they haven't really met even together. So that was very good. Alright, thank you very much for watching. I'll see you tomorrow. Bye!